Hello, happy children. It's time for another AP Chemistry video. And we've been sort of picking away at various topics in Chapter 8, beginning when we did the self-study unit. And so what we've spent most of our time talking about that's contained in Chapter 8 of our text is covalent bonding, and particularly in the form of drawing Lewis structures, calculating formal charges, and talking about the various resonance forms. But the chapter itself actually is concerned in general with the concept of bonding. And so there are a couple of things related to bonding that we haven't talked about in that chapter. One is the nature and the quantification of, I think that's a word, quantification of ionic bonding, and then also the concept of what's called bond dissociation enthalpy. So we're going to tackle both of those topics, and we're going to start with ionic bonding. And the first thing to do is just talk about something that I think we've talked about at various times before, and that's the concept of the Lewis dot symbol. Of course, we've talked about Lewis structures, but we can also talk about what are called Lewis dot symbols, and we've shown these before at various times. I think if you go way back to the beginning of the year, and we were talking about just thinking about compounds that form between various metals and nonmetals, we introduced the concept of the Lewis symbol. And it really takes the electron configuration we've been talking about recently and puts it in a more visual form by taking the valence electrons. And remember, the number of valence electrons is equal to the group number. And we're talking strictly about main group elements here in this slide. And it translates that into a symbol in which the valence electrons are represented as dots. And we've talked about the fact that you go all the way around with valence electrons, one dot northeast, west, and south before we start pairing them up. And this really gives us a visual understanding of a couple things. Number one, when it comes to ionic bonding, a metal, whether it be a group 1 metal, a group 2 metal, a group 3 metal, is going to ionize by losing all of its valence electrons in order to obtain the noble gas configuration of the previous noble gas. So all of these metals, sodium, magnesium, and aluminum, are going to ionize by losing 1, 2, or 3 electrons respectively to form so that they're isoelectronic with neon. It also helps us to see that nonmetals, whether they are going to bond by ionizing, that is gaining electrons, they will gain electrons so as to obtain the electron configuration of the next noble gas. Or if they're going to bond by covalent bonding, it gives you a general idea of how many covalent bonds they're going to want to form, because they're typically going to want to form one covalent bond for each electron that they are shy of a full octet. And so that's just the concept of the Lewis symbol. But now thinking about having actually ionized to form a cation or an anion, respectively, we just want to think about the idea of what is actually the nature of an ionic bond. Well, ionic bonding really is just the electrostatic attraction between oppositely charged particles. And so here's an image of a sodium chloride crystal, and these things are crystallizing in this fashion because the cations, in this case sodium ions, are being electrostatically attracted to the anions, which in this case would be chloride ions. And so we could also think about it in this way. An ionic bond is the electrostatic attraction between a positively charged sodium ion and a negatively charged chloride ion. They form this sort of lattice structure, but it's based on this electrostatic attraction. We could draw a similar thing for magnesium bromide. In this case, there are three ions in the formula unit of magnesium 2 plus 2 bromides, but they are being electrostatically attracted to each other. Calcium oxide is going to form between two ions, a calcium 2 and an oxide. And then sodium phosphate is another example of something. Here we've got 3 cations and 1 anion, but again, the driving force in forming a solid crystal out of these things would be the electrostatic attraction between a positively charged cation and a negatively charged anion. And so the measure of the strength of those ionic bonds is what's called lattice energy. And lattice energy is defined as the energy required to completely separate a mole of a solid ionic compound into its gaseous ions. And so by definition, lattice energy is going to be a positive endothermic number because it requires energy to take an ionic solid and vaporize it into its constituent gaseous ions. And this is really the this is something that is just completely governed by Coulomb's law. We've been talking recently a lot about Coulomb's law. And so the lattice energy, remember Coulomb's law in its energy form, in its force form, it's distance squared, distance between the two opposite charges squared. In its energy form, it's just a distance between the two opposite charges. And so the lattice energy is going to be equal to some constant, which just corrects for Avogadro's number and the charges on sort of the official SI unit of the charges here. Okay, so it's going to, the lattice energy is going to be that correcting constant times the product of the charges of the ions divided by the distance between them, which is going to be the distance between the two nuclei of the cation and the anion. And so here is a list. This is just table 8.2 from your textbook. But a couple things to note about lattice energies because of Coulomb's law. Lattice energies are going to increase with the charge on the ions. And so this whole column is lattice energies of compounds in which the cation has a charge of +1 and the anion has a charge of -1. And you can see that although they range, and we'll talk about why they all range in this neighborhood from about 600 to 1,000 kilojoules per mole. When you go to magnesium chloride and strontium chloride, which are examples of compounds in which the cation now has a charge of +2, you see a really significant jump from, so this is +1, -1, and they range from 600 to about 1,000. This is +2, -1, and now you can see that they range from about 2,100 to 2,300. If we now go to +2, -2, in other words, it's a +2 cation, a -2 anion, you can see that they jump up again because, again, the magnitude of the charges is increasing. Therefore, the lattice energy is increasing. And if we go to +3, -3, in the case of scandium nitride, you can see that it really jumps up significantly. The other thing to notice about lattice energies is that they are going to increase with decreasing size of ions. And so, or conversely, they're going to decrease as the ionic size increases. So you can see some what I would call homologous series here. Lithium fluoride, lithium chloride, lithium iodide, they all have the same cation, but the anions are getting larger, and therefore, due to Coulomb's law, because the distance is getting greater, that's in the denominator, the energy is going to go down. So the lattice energies go down from lithium fluoride to lithium chloride to lithium iodide. And you can see this again with sodium fluoride, sodium chloride, sodium bromide, sodium iodide. As the radius of the anion gets larger, the lattice energy gets smaller. Same thing with potassium, same thing with cesium. We can also conversely say, okay, let's hold chloride constant and look at the size of the cation. Lithium is smaller than sodium, sodium is smaller than potassium, potassium is smaller than cesium, and you can see that those numbers then, as we go from a smaller cation to a larger cation, are again going down, 834, 788, 701, 657. The same thing is true over here. Strontium is larger than magnesium, therefore the lattice energy is smaller. Strontium is smaller than calcium, calcium smaller than magnesium, so you can again see these lattice energies going down. An important thing to note, and this typically crops up on tests, and I've seen this not only on my test but on the AP exam, that lattice energy is going to affect physical properties. If you think about what the melting point of a particular compound is going to be, its melting point is going to be a function of the attractive forces between particles. And so you can see that if we take this series of sodium fluoride, sodium chloride, sodium bromide, sodium iodide, as the radius of the anion gets larger, the lattice energy goes down. You can see that the melting points also go down because it takes less energy to break these ionic bonds, and therefore the melting point is going to be lower. And then if you see that in the case of magnesium oxide, in which there's a huge jump between lattice energies of these +1, -1, and the +2, -2 magnesium oxide, you can also see there's a huge jump in the melting point. So lattice energy affects physical properties, and melting point is a typical measure of that. So what's a type of problem you could get related to ionic bonding and lattice energies? Let's read through this one. In ionic bond formation, the lattice energy of the ions blank as the magnitude of the ionic charges blank and the radii blank. Well, that can be a little bit difficult to parse, but let's think about this. The lattice energy is going to go up as the magnitude of the charge goes up. It's also going to go down as the magnitude of the charges goes down. So I'm looking for an answer or answers in which these two first thing are the same, right? So increase, decrease is going to be wrong. Decrease, increase is going to be wrong for C. Increase, decrease is going to be wrong for E, I'm sorry. So my answer, just in terms of the first two blanks, my answer has to be either B or D. Well, and they both say increase. So what about the radius causes a thing to increase? If the radius gets smaller, that's going to cause it to increase. So let's see if D makes sense. The lattice energy increases as the magnitude of the charges increases and the radii decrease. That is correct, and the correct answer here is D. Another question you could get, again, has to do with physical properties. Which compound below is going to have the highest boiling point? Well, if you think about charges, this is +2, -2, +1, -1, +2, -1, +2, -2, +1, -1. So our answer, we can rule out B, C, and E because A and D have the highest magnitude of charges, +2, -2, +2, -2. The thing with between those two, the thing with the higher boiling point is going to be the thing that has the smaller cation because it's the same anion in each case. The smaller cation between magnesium and calcium is magnesium. Therefore, the correct answer is D. What if I asked you which one has the lowest boiling point? Then you would go for the two which are +1, -1. That would be lithium bromide or sodium bromide. And because sodium is larger than lithium, that is going to have a lower lattice energy. Therefore, E would be the compound that had the lowest boiling point. All right, let's switch over to something completely different. We've just been talking about the strength of ionic bonds. Let's talk about now the strength of covalent bonds. And the simplest way to measure the strength of a covalent bond is by determining how much energy it takes just to break that bond in half. So the example that we're given here is a chlorine molecule, which is two chlorine atoms singly bonded to each other. How much energy does it take to just scissor that bond in half to give us two chlorine atoms? This is called the bond enthalpy or the bond dissociation enthalpy. And the bond enthalpy for a chlorine-chlorine bond, and that is represented as D, dissociation of chlorine-chlorine, that can be measured to be at 242 kilojoules per mole. So that's an example. That's what we're talking about when we talk about bond enthalpy or bond dissociation enthalpy. Okay, well, here is a table from your textbook again showing various bond dissociation enthalpies. They generally track, that is, the smaller the atoms involved, the greater the energy. And so if you see that a hydrogen being really small has a higher bond dissociation enthalpy than a carbon-carbon bond. But it doesn't always exactly track that way. So the trends are not exact like they are in lattice energy. And so you really do have to go to the table and just look all these things up. So this table is in your book. These are all single bonds. You will notice for multiple bonds that as the bond order increases, the bond dissociation enthalpy increases. So it is harder, it takes more energy to cleave a carbon-carbon triple bond than it does to cleave a carbon-carbon double bond. And it takes, and in fact, more energy to cleave a carbon-carbon double bond, 614, than a carbon-carbon single bond, which is 348. And these trends continue. A carbon nitrogen triple bond is stronger than a carbon nitrogen double bond. A carbon oxygen triple bond is stronger than a carbon oxygen double bond. A nitrogen, nitrogen, etc. And so these, again, these tables, both of these slides are from the same table. This table's in your text, and of course, on any problem that you've got on a test, these values would be given to you. So just to summarize, average bond enthalpies are positive values because bond breaking is always endothermic. And so that's the same. Bond dissociation enthalpy in that sense is the same as lattice energy. It's a positive value because you're breaking things apart. An important thing to recognize is that these tabulated bond enthalpies are average enthalpies for each given bond, but not exact. And that's because not every CH bond is identical. You can have a CH bond in an infinite number of compounds. And so these are average bond enthalpies. And then just as we were saying, double bonds are stronger than single bonds, triple bonds are stronger than double bonds, etc. Well, there is no etc. That's just, that's what it is. Okay, what is the use of these bond dissociation enthalpies? They can actually be used to approximate enthalpies of reaction. Now, back in chapter 5, we talked about using standard enthalpies of formation to determine enthalpies of reaction. But if you didn't have the standard enthalpies of formation of the specific compounds you were interested in, if you were presented with a reaction and asked to at least estimate the enthalpy delta H for that reaction, but you didn't know exactly the standard enthalpies of formation for every component of that reaction, you could use a bond dissociation enthalpy table to estimate that. And we would do that by saying, well, delta H for the reaction is going to be the sum of all the energies that we have to put into breaking all the bonds that we're going to break. That requires energy, minus the sum of all the energies that we make to get the products, because making bonds releases energy. So when we take all the energy that we put in, subtract out all the energy that we get out, we're going to get delta H for the reaction. So we're using as an example this reaction, the reaction of methane with chlorine to give methyl chloride plus HCl. And what are we doing to get to there? Well, we're going to break a CH bond, and we're going to break a Cl-Cl bond. And then once having done that, we're now going to make a CCl bond, and we're going to make HCl bond. So methane plus chlorine to give methyl chloride plus HCl. We're breaking a CH and a Cl-Cl. We're making a CCl and a ClH. Okay, so let's check the energetics of that. The delta H for that reaction is going to be the sum of the energy that's required to break a CH bond and a Cl-Cl bond, minus the sum of the energy that we're going to get back by forming a CCl and an HCl bond. If we went back to the table, we can just substitute in these values. Again, in a problem, you would be given these values. You're not expected to know them. And when we evaluate that, we get 655 minus 759, and we get a delta H for the reaction of minus 104 kilojoules. Is this exactly the value of delta H for this reaction? It is not, because this is the value of an average CH bond. A CH bond in methane may be slightly different from that. This is the average CCl bond. A CCl bond in methyl chloride may be slightly different than the average, but this is going to be very close to what the actual answer is. Okay, no, one more slide. I'm sorry. Just a quick comment about bond length. We've talked about the fact that that higher order bonds are stronger and require more energy to break. They're also shorter. And so you can see on this slide that in comparing the length of a carbon-carbon single, double, and triple bond, as the bond order increases, the bond length decreases. That's true in every case, whether it's carbon-carbon, carbon-nitrogen, carbon-oxygen, nitrogen-nitrogen, nitrogen-oxygen, oxygen-oxygen. As bond order increases, the bond length decreases. Okay, I think that is the last. Yes, that is the last slide. Thanks for watching, and I look forward to seeing you in class. Bye-bye.